Welcome back, everyone. Let's just jump right into today's explainer. We are taking a fascinating journey into classical mechanics to completely demystify the elegant rules governing the simple pendulum. You've seen pendulums everywhere, right? From the grand old clock in a hallway to a kid swinging on a playground. But beneath that simple, mesmerizing back and forth motion lies a really beautiful hidden architecture of physics and mathematics. By the time we finish up here, you aren't just going to know how a pendulum swings, you're going to understand the exact mathematical heartbeat that drives it.
Here's our roadmap for this explainer. First, what is a simple pendulum? Second, mapping the forces. Third, proving simple harmonic motion. Fourth, deriving the time period. And finally, calculating the frequency.
All right, let's kick things off with section 1. What exactly is a simple pendulum?
When physicists talk about a simple pendulum, we're actually talking about an idealized model. This means we have to imagine a perfectly abstract scenario to make the core physics clear, basically stripping away the messy realities of the real world. So this ideal model consists of a point mass, meaning literally all of the mass is concentrated in a single infinitely small dot, suspended by a completely weightless, inextendable string, and hung from a fixed, totally frictionless pivot point.
Now, to get a real-world pendulum to even closely approximate this ideal model, we have to meticulously follow a few specific rules. We have to make sure the bob, the actual weight at the bottom, is really small compared to the length of the string, which we'll call L. Plus, the mass of the string itself has to be practically zero compared to the bob's mass. And this is crucial. The cord has to remain perfectly straight and not stretch whatsoever. If the string acts even a little bit like a rubber band, our pendulum suddenly becomes a spring, and all our elegant math goes right out the window.
Moving right along to section 2, mapping the forces. Imagine pulling that pendulum bob to the side and just letting go. Assuming no air resistance, it swings back and forth. But why exactly? Well, look at the hidden geometry here. You can clearly see the weight of the bob pulling straight down due to gravity, which is mass times gravity, or mg. But because the bob is hanging on an angled string, that downward weight vector splits. It gets resolved into two distinct components using the angle theta. The first component is mg cosine theta, pointing directly away from the pivot, and this one is completely balanced out by the tension T pulling back up the string. They literally cancel each other out. So that leaves our second component, mg sine theta. Since it points back toward the center equilibrium point, essentially fighting the displacement, we add a negative sign. This negative mg sine theta is our true restoring force. It's the invisible hand constantly pulling the pendulum back to the center.
Which brings us to section 3, proving simple harmonic motion, or SHM.
Let's see how this builds step by step. We start with that restoring force we just mapped out. Force equals negative mg times sine theta. To make this work, we're going to use a brilliant physics trick called the small angle approximation. If we only pull the pendulum back a very tiny amount, the curved path it takes, the arc length s, is basically just a straight horizontal line, exactly matching our displacement x. When that angle is small enough, the sine of theta essentially equals the opposite side over the hypotenuse, which is displacement x divided by the string length L. If we substitute x over L in place of sine theta, our restoring force equation beautifully simplifies down to force equals negative mg times x over L.
And here is where the magic happens in step 3. Let's bring in Sir Isaac Newton. Newton's second law says force equals mass times acceleration, F equals ma. If we set Newton's formula equal to the restoring force formula we just built, we get ma equals negative mg times x over L. Just look at both sides of that equation for a second. The mass m is on both sides. That means it completely cancels out. We are left with acceleration a equals negative g times x over L. Now remember, gravity g is a constant, and the string length L is a constant. Therefore, the acceleration is directly proportional to the negative displacement, negative x. And friends, that right there is the exact, strict mathematical condition required for an object to be executing simple harmonic motion.
Section 4 already, deriving the time period.
Because we just proved it's executing simple harmonic motion, we know its acceleration absolutely must match the universal formula for SHM, which is acceleration equals negative 4 pi squared over the time period squared times displacement x. On step 2, we take our specific pendulum acceleration we just found, negative g over L times x. In step 3, we just equate them. The negative signs cancel out. The displacement x on both sides cancels out. We're left with g over L equals 4 pi squared over t squared. With just a little bit of cross-multiplying and taking the square root of both sides, we reveal our grand takeaway in step 4. The time period t equals 2 pi times the square root of length over gravity.
This elegantly simple equation tells us exactly how long a pendulum takes to complete one full swing.
Finally, Section 5, calculating the frequency. Time period and frequency are basically two sides of the same coin. Time period is seconds per swing, whereas frequency is swings per second. Since frequency is mathematically just the reciprocal of the time period, literally 1 divided by t, it is so incredibly satisfying to just visually invert the formula we just worked so hard to derive. You take the time period formula and you just flip it upside down. The 2 pi drops to the denominator to become 1 over 2 pi, and inside the square root, the length and gravity trade places. So frequency f simply equals 1 over 2 pi times the square root of gravity over length.
We've covered a ton of ground today, from theoretical definitions to algebraic proofs. But before we wrap up this explainer, I want to leave you with this highly surprising physics takeaway to ponder. Look closely at those final formulas we just derived. Time period depends on the length of the string, right? It depends on the gravity of the planet you're currently standing on. But do you see m for mass anywhere in those final formulas? No. Since the mass of the bob completely disappeared and canceled out during our proof with Newton's second law, it has absolutely zero effect on the swing. So, assuming our ideal conditions, does a massive 100 kilogram weight swing any faster than a tiny feather hanging on the exact same string? The math says absolutely not. They swing at the exact same rate. Let that counterintuitive reality sink in for a bit. Thanks for joining me on this explainer, and keep exploring the fascinating mechanics of the world around you.